Okay, continuing on with class number 17, we began talking about lift and drag, and we went kind of a side little trip talking about the boundary layer and laminar and turbulent flow over slender and blunt bodies. And if you'll recall, one of the discussions that we said, without knowing the pressure and the shear distributions, we really can't find the drag and the lift. So we're sort of kind of stuck. We don't know exactly how this pressure and how the shear, how that's distributed along the airfoil or whatever object that we're trying to find the lift and drag for. So because of that, we use a Buckingham pi dimensional analysis, which we just covered in the previous classes. And we do that for either lift or drag, because they're both forces, and we look and see what they're functions of, which is going to be speed, the flow speed, or the flow of the object within the fluid, the density of the fluid, viscosity of the fluid, and then some dimensions. So it might be the length of it, it might be the width of the part. There's going to be more than one dimension. There could even be other things besides these. Like we could think, well, maybe the speed of sound, because we might be concerned about changing into compressible flow region. We might want to see the roughness as well, because that could influence the changing from turbulent to from laminar to turbulent. So there's some things that could also depend on, but just as a base number of variables, this is what we're going to stick with, right? So for the general case. So we take a look at all the different dimensions of each of these, and we know both the lift and the drag are force. So we could do a single Buckingham pi dimensional analysis for just one of them, and it'll apply to both. So we have the speed, and we have the density. I'm going to go ahead and use FLT because the main parameter I'm looking at is a force, so it makes sense to use the FLT system. So we convert the density into an FLT. And then we could just pick for the dynamic viscosity FLT. And then, of course, I guess I didn't put it down here. I guess I have the width as being the length, but also the length is the length. So that's kind of obvious. And so we end up with three. We used all three terms, and we had five variables. So therefore, we're going to have two pi terms. We can expect two pi terms. If we had more variables, we'd expect more pi terms, obviously. But some of those would be just ratio of maybe the roughness to one of the lengths, or it might be the velocity, the velocity and the speed of sound. So that would be Mach number. So, but we would get other pi terms, but here are going to be the main two pi terms. And so I'm going to choose repeating variables as being the speed, the width, and the density. We could just as easily have picked the length instead of the width, but just from experience, we might want to choose one or the other. But here we're going to use a generic width. Sometimes this could be diameter as well, right? So step 5, we do our first pi term, which is going to be based on that main variable, the drag, as what I'm using here. But again, it could have been lift, didn't matter. And so going through this little table, we could see, first off, we could see that C is going to be equal to -1. Right, that's going to be pretty obvious. And then for the next one, we're going to have A plus B minus 4C. But of course, remember that C was -1, so that's really going to be A plus B plus 4 equals 0, or A plus B is going to equal to a -4. And then we go down and we see of negative A plus 2C is equal to 0. Well, negative A, and then so we're going to have minus A, and then of course 2 times a -1. So we get A is equal to -1, and then we see that B is equal to -1 based on that previous equation. So if we plug all these back in, we have this drag force divided by the speed squared, the width squared, and the density. And if you look at this bottom, well, let me see. I'm going to finish up with my Buckingham pi. Yeah, that's right. Let's not give it away yet. So we're going to step 6 is to do it for the other non-repeating variable, which is going to be our dynamic viscosity. And let's just look through there. We see C is also -1 as it was before. We get A plus B is going to be -2. And then we end up seeing that we have A as a -1 and B as a -1. And if we plug those back into as the exponents, we get mu over U W rho. But if you look at that closely, you'll see that that is actually Reynolds number upside down. So we might as well flip it over, because this is a non-dimensional number, so it doesn't really matter whether what's on the numerator and the denominator. You could flip it either way. It's just going to be the inverse of the thing. So it's just, but we know that to be an important parameter. So we do the check, and we find that both of these are dimensionless, and so we do our final step here. But what's really important to look at is this, the first pi term and what that actually represents. First off, we end up calling that pi term the, well, with a little bit of a change. Well, first off, because we recognize what's on the bottom, that's Bernoulli, right? Just like you have 1/2 rho v squared, we have rho times u squared, which is rho v squared, and that W squared is kind of representing an area, the area that, and this is like a dynamic pressure acting onto an area. So we go ahead and stick the 1/2 in there, because that's going to, we're thinking of this as dynamic pressure times area. And therefore, what we're left with is this drag, we call that the drag coefficient. So the first pi term, merely adding in the 1/2 and deciding that that W squared is the representative of it being an area squared. And we have this drag coefficient. And just the same way, we have the lift coefficient, right? So here's where the drag coefficient and the lift coefficient come from. And if you recall, the whole idea of using the non-dimensional approach here is that we can run experiments. And if we can match all the things up on the right-hand side from the experiments that we're running, if all of those match up, then we can have the model that we're running match the real thing. So if we get these to equate with whatever the things we're comparing, we're able to get to this to equate. So if we run some experiments according to the idea behind this, we can develop some coefficient, a drag coefficient or lift coefficient that are dependent on these parameters. You can see there's Mach number, Reynolds number. Here's a roughness ratio. And this Li over L, that's just is a generic, some type of dimensional relation parameter, like a scale of width to length or something along those lines right there. So how this works is that area usually for the drag is different from what the lift is. And the drag, it's going to be what we call like the frontal area. And I think that the best way to think of that, or the way I think of it, is to take a flashlight and shine it on the object and then look at its shadow. And that's going to be, so from the direction of the flow, that's going to be the drag area. So in this case, it's going to be the diameter of this cylinder times the length of that cylinder. And that's going to be the frontal area. And that's what gets used down here in the drag. And then, for the lift, it's going to be the planform area, right? So that's going to have like having the flashlight pointing down at it and seeing the shadow that's beneath it, right? So and then that like flashlight is like perpendicular to the flow direction or velocity direction of these two things. And what we end up with from experiments is we find a whole lot of different charts and figures that we can look through to try to find them. All right, so here's just a summation. I think I'm being repetitive, but if you want to find the drag, look up what the drag coefficient is and multiply by 1/2 rho v squared, and then the frontal area. If you want to find the lift, do 1/2 times the lift coefficient that you've looked up in a table or a figure, and times the density, the velocity squared, and then the planform area. And we note once again that 1/2 rho v squared is the dynamic pressure. So this is really just dynamic pressure times an area. and with a correction factor. You could think of the drag coefficient and the lift coefficient as correction factors for trying to have that pressure times that area to equal the force. And it's for a lot of different reasons. And these are all empirical, but you could kind of think of them. Some of this is actually can be viscous shear, and some of it can be pressure. Some of it could be the idea that like the pressure isn't acting right up against a plate. So if it's a slender object, it's going to be a much smaller drag coefficient because it isn't like hitting the thing straight on. I think I'm going to be a little more repetitive here, coming on to the, so what was the last thing? No, nothing. Okay. Oh yeah, something that I did want to bring out that I don't think I wrote down in class, but I think I had a space for it, but I just didn't write it down. Remember that when you want to get the power of a vehicle due to drag, or power in general due to thrust, or something along those lines, you can multiply the force times the velocity, and that will give you power. Right. So if you want to try to figure out how much power you need to overcome a drag, you could just multiply the drag force times that velocity. So that's a really important outcome that we would care about. There you go. So I didn't bother doing the animation for this one, but we're kind of really repeating myself where I'm saying there's the drag can have two parts. It can have a pressure drag and it can have a friction drag. And here's another picture of that in terms of the concepts there. And here's for the blunt body where you're having that friction drag. It's taking place around like the first bunch of it, right around where the flow separation takes place is what they're saying. And here's the pressure drag, and so we're showing that on like a car, and you can kind of see on the hood of the car. And there's actually going to be some lift taking place of these low pressure areas. That's kind of interesting onto the thing. So that's a negative pressure. Of course, here's a negative pressure that's kind of, and this will be holding the car downwards, right? And there's a negative pressure behind the thing. So the distribution of pressure is something that you could be interesting to think of, and how it plays a role in drag. And one aspect I had mentioned in today's class when we went through this lecture is like the idea that you can have trying to get this out. I'm sorry, it's late at night. Where you could draft, right? When you have drafting, because you could be back in the low pressure zone behind a vehicle, and you could avoid some of the pressure drag that you would be feeling if you were out in front. So that's sort of like the idea behind drafting behind a vehicle is if you get into their low pressure region, you can reduce your amount of drag. All right, and so there's lots of shapes and speeds and that when we're looking at the charts and the graphs. So we have lots of graphs and charts. My first question here is we have this little tiny body right here with a diameter d, and then we have that's just a circle. And if you take a look at the streamlined a piece right here with has a dimension that's 10 times that diameter. It's amazing to think that these both have the same drag, and that's what they're saying up above. But if you take a look at this drag coefficient chart here on the left, notably the Reynolds number is on the horizontal axis. Also note that the drag coefficient right here is on the log scale. So these are both log scales. But if you take a look for that round circle right there, it gets pretty kind of flat, and then there's like a dippity-do. That's sort of an important little dippy-do to take note of. But let's just say we're in the range right up in here. So we're, let's see, we're 100,000. You come down to this airfoil shape. So this shape that's right here, that's more streamlined and looking at the piece, and you can kind of see how much smaller that drag coefficient is to this circle up above, right? This one is somewhere like 1.5 0.5 or something along those lines. I'm not quite sure what it is. I don't know if I want to guess what it is. It's close to 1. It's a little higher than 1. But if you come down to the airfoil down here, we could see that it's going to be much smaller, probably by 0.05, 0.07, something like in that range right there. So much smaller. I was trying to think of other things I wanted to point out right here. We can also, we can make an ellipse out of this. And so over here, we're having a little demonstration of like the proportions of that ellipse and whether something's parallel to the flow or whether it's perpendicular to the flow. I think that's what we're looking at right here. Yeah, it depends on whether you were talking about the diameter here. We're talking about the length, right? So those are the two separate curves. But you can see that if this flat plate normal to the flow, we get like about 1.9 is what I see people interpreting that point as. We can also notice that when we get the proportions that are L over D is equal to 1, right over here we get a drag coefficient. I'm going to say it's going to be a little bit greater than 1 because we're saying that right up here. When it's a circle, it should be a little bit greater than 1. Here's from another book. I believe this is from Sengel. And all this other stuff has been from Munson. And we can see that the drag coefficient is the statement that the drag coefficient for many objects stays pretty constant of above about 10,000. A Reynolds number of about 10,000 right there. And they're saying that this for many geometries, but not all. And one notable one are spheres. So spheres have this dippity-do, as I referred to it before. That's pretty interesting because when you get down here, the drag coefficient drops. And you'll notice that it does stay kind of constant for a little while up to this point right here. Well, this is one of the reasons why golf balls have dimples, because we want to try to shift and move this reduced drag coefficient over to the left so it occurs at a lower Reynolds number and therefore a lower speed, right? So that's why do golf balls have dimples? Because we can have this dippity-do. Now you ask, what is the dippity-do caused by? And it really is because of this flow separation as this let's see, we're talking about the sphere, right? So it's the solid line right here. As we move along down here, of course, this is for the cylinder, but these little points, these little markings, but let's take a look at it. And as that separation point, right, there's no separation starts, we start to get this vortex things taking place, and that it starts to the wide turbulent wake starts to narrow down and becomes this thinner turbulent wake. What also happens is the boundary layer gets thin, and the boundary layer you could think of as the thing that's kind of caught, we have frictional drag and we have pressure drag, but there's sort of a pressure drag that's caused by that boundary layer. Right, you just kind of think of the thing got thicker because of the boundary layer, and now that is the zone. This fluid that is following along with the object. It's now gotten smaller when it gets to this little region, and that's that E region right there. So it's gotten smaller. So now all of a sudden its drag coefficient has gone down. But we can encourage that to happen earlier if we have the dimples. So the dimples encourage that helping turbulence. And so you can see here in this, this is sort of a zoom in of that region where here is where the dippity-do takes place. And I wish I had moved this guy. Let's see. Can I move him? I don't think I can move him. I think I actually that's part of I did a copy and paste and put it in as a picture. So I think that's like stuck in there, but I should move this around so you can see what these Reynolds numbers are that are below there, so you can kind of see where they correspond. But you can see where the low spot is right there, where that corresponds. But you can see that with the increased roughness, and these are these other dash dot curves are all increased roughness. And here's the golf ball dimples that have actually caused the dippity-do to shift to the left and to reduce the amount of drag. like just a couple more things. I know I'm at the 19-minute mark. We'll do the examples after this. One important part about the drag and the lift, I guess, when we're talking about a body that's this sphere or a cylinder, is we might have rotation. And some of that separation point that we're looking for, that's right up here, can be shifted away from being in line with the flow if we're also spinning. So remember, we have that zero slip at the boundary of the fluid. Well, that also works when we're talking about a rotation, right? So the rotation is moving around. If this thing is spinning, it's also creating a field. So when you superimpose these two things on top of each other, we have the stagnation point actually moves over to the side. And so also the separation point, of course, this is we're looking at the uniform, no separation thing taking place here to try to identify the stagnation point. So a similar thing is taking place when we have the boundary layer type flow and we're having that flow separation point and shifting over. And that, because it's non-symmetric, that's going to cause a zone of higher pressure, and it's going to cause the motion. And that's the idea behind a curve ball or a golf ball spinning. And like if you're a slicer, you can definitely see the arc of the ball as you've hit it and sliced across the face of the ball, causing a side spin. But also, if you're a really good golfer, you could probably create backspin that will change the shape of the shot. You can also have front spin too. But people who hit a draw or a fade, they have put just the right amount of spin to be able to control the trajectory of the ball. And that's a pretty amazing thing, and I wish I could do it. More pictures. This is out of Sengel. This guy's out of Munson. This figure right here, this is out of Sengel. So I'm not sure why I put this in there. Right there, and then repeating. Oh, here's where I had the CFD, where I'm showing this formation. So these are little illustrations in the book, Munson's book, but here they are, and you can see that I start out with a Reynolds number of 1, and then move to 10, so that corresponds to B. Then I move to 100, which kind of corresponds to C. Don't quite have that vortex yet. And then we have, so now we have the vortices that are happening when we're at a Reynolds number of 1000. And that's really what we consider boundary layer flow, by the way. And then we start to see what's taking place at 10,000. And so that's pretty close to being D, where we start to get that separation. You can kind of see it better at the 100,000 than that. And now at the 500,000, that's where we really see the narrowing of the wake behind it. And we have a much thinner boundary layer, and we're getting some of the benefits of having made that boundary layer much smaller. And we're still in that zone. It's kind of neat how you can see some of the swirling going on. And then you can see that we're crawling back out of there, where we're not nearly getting the amount of benefits from there. So maybe some of the shear is starting to overcome what's taking place in there. So let's see. Here's more shapes, and we'll be using some of these. There's some more in your textbook. Notably, things to take a look at is that these all are associated with an area, and they're associated with a range of Reynolds numbers. See, a lot of them are going to be greater than 10,000 is what they're saying. You might even have a difference in direction, right? For this hemisphere versus this hollow hemisphere, you can see you have a different drag coefficient, and you would want to take a look at these and try to make them make sense. I guess one last thing, as I'm at the 24-minute mark, we will have the Froude number is also an important thing. Well, it's an important thing for ships. If you're interested in ships, there's something called a bulbous bow. And a bulbous bow, what it does is it creates sort of this anti-bow wake. It's sitting just below the waterline, and it kind of creates its own wave that counteracts the main bow wave. And what it overall does is helps to reduce the amount of drag on a hull, especially right at a design speed. So it's made in the right size for the design speed so that you actually create this, like I said, an anti-wave. You're kind of thinking about it like making a wave that's completely out of phase with what the bow wave will be, and therefore you're reducing this wave size. And the Froude number is all about trying to put relating to gravity wants to keep the water flat, but the ship wants to push the water away, and so it's this interaction with the free surface of the water that's causing this resistance. The whole resistance is, a lot of it is about, like, sometimes we call it wave making resistance. So that's like an important thing, because we want to try to push water out of the way. So that's a really long video, but I hope to maybe, if people are going to be doing some review, this might be a little bit of help, or if somebody was sick, I got it down. So thank you, and we'll continue with some examples after this.